Alright, so in this particular video, we're going to introduce and walk through one instance of a gate that's actually, in this case, applicable to both classical and quantum computing. This gate that we're going to be considering here is known as a controlled NOT gate, or oftentimes abbreviated to CNOT. Now, this CNOT gate is best illustrated using a table which we have so handedly kind of drawn on to the right of the screen here. Now, in considering our possible inputs and outputs, the CNOT gate, our controlled NOT gate, essentially has two inputs, and we'll label them X and Y, and there's two outputs, we'll label them X, and in this case X with our little symbol corresponding to a particular gate here, and Y. Now, if you note here, the number of inputs here is actually going to be equal to the number of outputs, and this will actually allow us to make a number of observations. So I do want you to keep that in mind. And so when we consider our inputs, recall that our inputs in this case are going to be bits of some sort. Now, for the most part, if we talk about bits, right, they use what is known as binary notation, and as a result, we only have two possible values for them, 0 and 1. So we can consider all possible inputs, and we have pairings, possible input pairings, here. And so we have 0, 0, we have 0, 1, and we have 1, 0, and we have 1, 1, just systematically moving down the line here. Now, our first bit in this case, our X, in this case, we'll call our control bit. And the reason it is known as the control bit is it determines whether or not this NOT gate here will be applied. That's why it's known as a controlled NOT gate. And so when the value of our control bit, when the value of our X here is going to be equal to 0, what we do is we do not apply the NOT gate or the NOT operation to our second bit, our Y bit. When the value of X is going to be equal to 1, on the other hand, we do indeed apply the NOT operation. And recall the NOT operation, for the most part, what it does is it reverses or inverts the value for our particular value. So if Y is equal to 0 and we apply the NOT gate, and the value of NOT Y is going to be equal to 1, and the opposite is true when Y is equal to 1. And so walking through our various examples, we first have X is equal to 0, and we also have X is equal to 0 for our second row as well. And so as a result, what occurs is we preserve our X value here regardless of where in this table we are. Is worth noting that. But what we say is, hey, because X is 0 here, our Y value is going to remain unchanged. And so as a result, our Y value is going to stay 0 for the first row and 1 for our second row. Now we look at our third and fourth rows where X is equal to 1. We note that we will indeed apply the NOT operation here. And so the NOT of Y for our third row is going to be equal to 1 because the opposite of 0 is 1, technically speaking. And of course, for our fourth row, the opposite of 1, from a binary point of view, is going to be equal to 0. So looking at this particular table here, we can make a number of observations. First of all, we look at pairings between our inputs and our outputs, right? We note that for every possible input, there is only one output that corresponds with it, which is quite obvious in this case. However, if we're to work backwards, we see that for every possible output there is only one input that corresponds to it as well. And what that means is we can essentially look only at the output without knowing what the initial inputs into our gate were, and say, hey, I recognize this output, and I know and can deduce or reverse engineer the process that has occurred here in order to understand and determine what the particular input was. And this actually constitutes what is known as a reversible gate. And this is actually a concept that has its own implications within the realm of quantum computing. However, a reversible gate, what it does is it allows you to work this gate in both directions. No information is lost, saying, hey, if I'm given only the input, I can determine what the output is. If I'm given the output, I can also determine what the input is as a result. Instances where a reversible gate is not applicable is, say, with using the AND operation, where if you were to find the AND of two particular bits, we do indeed lose some information as a result, because this one output can map to multiple possible inputs, and that makes it not a reversible gate. Now, seeing that as this is, we can actually draw a number of other things, and in this case, we can actually notate it using a bit of a function notation. Now, let's say we name our function f in this case, and we say our inputs are x and y. Note, I've again noted and mentioned that our first bit here, our first input, is going to be known as our control bit. And here the order will indeed matter, and you could just rewrite it, and the resultant output corresponding to our inputs, our function here, is going to be equal to x, comma, and then our particular operation here. And so with this kind of in mind, there are a couple things I do want to look at in a bit of a closer kind of under a magnifying glass. And so let me briefly clear the board here and rewrite the function at the top. Alright, so now that we have this particular function, what we can do is we can attempt to visualize what is occurring using a circuit of some sort. Now recall a circuit, right, describes, for instance, the traveling of electricity through some given gate of some sort. And typically what we can say is, hey, our inputs here are going to be x and y. Right, and so for our x value, you will note that the x value here is preserved, and so we're just going to finish this line, draw all the way through, and say, hey, one of the outputs for this particular circuit here is going to be x. However, it is worth noting that the x does have some control over our gate, and so what we're going to do is we're going to draw a bit of a node here and say, hey, we're going to pull the x down and draw what is a exclusive OR gate. You will notice our particular symbol here, right? And we're going to say, hey, this is going to give us our particular output of x and y in this case. And so this is actually a corresponding circuit that helps us visualize what is occurring here. So if you note, we have our two inputs. We have our first input, our control bit, our x, and we have our y input, our second input. And so our two resultant outputs are x, and then our x and y kind of once it has passed through this particular XOR gate. And so this is what it looks like just from a visual perspective. If we were to simplify this particular circuit diagram that we have here, just really briefly saying, hey, what is occurring here? Again, we have our x, we have our y values, and what we can do is we can just draw again just another node and say, hey, we're going to use our symbol here. This is our y input, I apologize. Say, hey, it's going to give us an output of this. Alright, and so this is kind of a simplified circuit diagram if you do want to visualize what is occurring here. Now, before we jump into how this applies and what this looks like in the context of quantum computing, let's really briefly talk a little bit about notation. So up until this point, we've used the idea of certain standard bases. In this case, the standard bases for a quantum computer is going to be 1, 0, and 0, 1. We've quite briefly actually also mentioned, and perhaps if you've read through several textbooks, or if you're just coming from a slightly different place, you may recognize that this actually corresponds to measuring the qubit in directions of spin up and spin down, right? And so what we do oftentimes when drawing an analogy or trying to draw connections between this and the classical computers is say, hey, our spin up bit, if we were to measure the qubit with spin up, we're going to say, hey, that corresponds to value 0, and if it measures and comes out to be with the direction spin down, we say, hey, that comes out to have a bit of a value 1. And so just for I suppose convenience's sake, what we can do is we can say, hey, let us rename the bits. We're just merely renaming them in this particular case to be 0 and 1. So this will help us actually mathematically visualize what is occurring. Now, if we were to say, hey, what happens if we are considering, for instance, a multi-qubit system of some sort? What occurs is that the bases with which we measure the multi-qubit system, say, for instance, a 2-qubit system, will look something along the lines of this. So typically, these concepts are first introduced, we utilize what is known as the tensor product drawn between our qubits, and that just essentially puts them in the same system, allows us to relate them accordingly. And so we have the tensor product of 1, 0, 1, 0, and then we have the tensor product of 1, 0, and 0, 1, right? And then of 0, 1, and 1, 0, and lastly, 0, 1, and 0, 1. And so if we were to follow through with this general convention here and rewrite it using what we have where up corresponds, or I suppose 1, 0 corresponds with our 0 bit, or you can say, hey, this is equal to the tensor product of 0 and 0 are 0 vectors, and then we have a tensor product of 0 and 1, and you have the tensor product of 1, and I apologize, I'm running my 1 in 2 different ways here, out of pure habit for different purposes. 1 and 0 in this case. And let me make sure we have some consistency at the very least. And we have 0, I apologize, 1 and 1. 1 and 1, the tensor product of that. Alright, and so looking at this, what we can do is we can actually break it down a little bit further, and what we've possibly done, and just say, hey, we're actually going to imply that we're finding the tensor product of particular vectors in this case, merely through the just juxtaposition of where we place these vectors. And so we can say, hey, you know, we have just our two 0 vectors placed right next to each other, our 0 and 1 vector placed right next to each other, and then our 1 and our 0 vector placed right next to each other, and our 1 and our 1 vectors placed right next to each other. And again, juxtaposition, this is purely for notational purposes. And from there, what we can do is we can go back to this particular table that we drew concerning our controlled NOT gate. Alright, so we have a familiar table corresponding to our controlled NOT gate over here. And what we could do is we say, hey, you know, we have our input values, we have our output values, and they each correspond to either 0 or 1 for individual bits. And what we can do is actually rewrite these using vector notation, just add a little bit of a vector kind of symbol around it. Now, looking at what we have here, this allows us to make several observations. First of all, if you take a look at what is occurring here, we can in fact rewrite the particular system that we have on our hands. And let me briefly make sure everything down. Alright, so now they're written as vectors, we could actually simplify this down and actually essentially compact it just by a little bit more by putting our two corresponding vectors for input and our two corresponding vectors for output together. And so what occurs is we take our first input and our second input, and what we can do is we can actually remove this kind of dividing line here and compact it down into a single vector representation of some sort. And in this case, our vector representation here would be 0, 0, right? And then which corresponds to an output of 0, 0. And then we have input of 0, 1 in this case, which corresponds to an output of 0, 1. And then we have our 1, 0 input, which corresponds to an output of 1, 1. And then we have our input of 1, 1, which corresponds to an output of 1, 0. And if you know, again, the order here does indeed matter. Again, the first value within our particular vector corresponds to our first bit, our control bit, and the second value corresponds to our second bit, our y bit in this case. Now, looking at what we have here, now that we've written it fundamentally in vector notation, what we could do is say, hey, let's move this table to the side and actually write it using and essentially as a linear combination of what is occurring. So our input value of some sort is going to be equal to, let's use our STU as our probability amplitudes here. So we say, hey, you know, we can actually rewrite it, the entire qubit system as essentially R 0, 0 plus S 0, 1 plus T 1, 0 plus U 1, 1. And what we're doing here is we are actually to this entire probability amplitude, to this entire linear combination here, to this qubit model that we have here, is we're applying what is known as the controlled NOT gate, which actually gives us the resultant of, I suppose you could say, which gives us a value of R of 0, 0, because again, our output here, right, this each one will correspond to its output, S of 0, 1, right, plus T of 1, 1, plus U of 1, 1. Let me rewrite. There we go. All right, and so what occurs here is, as you can see, the CNOT gate is changing the particular vector that it corresponds to. It's permutating it. And what it does is essentially says, hey, for every particular input, right, what occurs is we're going to actually connect it directly to its output while preserving the probability amplitudes. That is essentially what we're doing here. And you will note, actually, oops, and let me make sure this is correct. There should be a 0 back here, right? And what occurs, what we can see here, is essentially that I suppose you could say the probability amplitudes for 1, 1 and 1, 0, or T and U here were merely switched. Therefore, to move this around and put it back in the order of 0, 0, 0, 1, 1, 0, and 1, 1, you will note again that the U and T probability amplitude placements have been switched relative to one another. And so, using this diagram that we earlier had, that we earlier established for our particular CNOT gate, referring to, for instance, our input X, right, and our input Y here, here is our gate. And we have, again, our output here, our second output up here. Right, looking at what we have here, what we can actually do is we can replace these inputs and outputs with their corresponding vector values, which allows us to visualize what is occurring from a more mathematical perspective. Now, if we were to, just for perhaps just mathematical purposes, or for instance, say, hey, you know, what can happen in a particular situation, let's consider one instance where we take our top qubit of some sort, and we're just going to remove their names for now. We will no longer refer to them as X and Y. We'll say this is our top qubit, this is our bottom qubit. Let's say we measure our top qubit. Oops, and that should be bottom. Cannot spell for the life of me. Bottom qubit. There we go. Right, and we measure our top qubit, and it gives us essentially a probability amplitude of 1 over root 2. Let's say we have 0 in this case, plus 1 over root 2, and 1. Right, and we measure our bottom qubit of some sort, and we know that its corresponding value is going to be 0 in this case. And so we look at it and say, hey, what would this look like in terms of the particular outputs? Let me make sure there's a note here. All right, in terms of its outputs. Now, from a mathematical perspective, what essentially is occurring is we're saying, hey, you know, we take an input qubit of 1 over root 2, 0 plus 1 over root 2, 0, and we essentially find the tensor product of that with our second qubit here, our 0 vector in this case. And what ends up occurring is we can rewrite this particular tensor product as being equal to 1 over root 2, 0, 0, plus 1 over root 2, 1, 0. Now, looking at what we have here, we say, hey, you know, this actually helps us describe the possible states that our qubit can have. 1/2 of the time, which is equal to 1 over root 2 squared, right? Our probability squared gives us the probability of getting this particular state. 1/2 of the time, both qubits will come out to be measured to be 0, and 1/2 of the time, one qubit, the first qubit, will come out to be measured as 1, and our second qubit come out measured to be 0 in this case. One sec. However, what we have to do is we have to apply what is known as a CNOT gate to this particular linear combination. So just to clear this, to avoid any confusion, we now apply our CNOT gate. Now, recall what we said earlier, what happens to a particular CNOT gate in this case. But, one way other than saying, hey, we switch the probability amplitudes, is saying, hey, we change the value. So when we apply our CNOT gate, the resultant value, I'm going to go towards the left in this case. The resultant value is actually going to be equal to 1 over root 2. And for our 0, 0, right, the resultant probability amplitude here still remains the same. So we have 0, 0. Right, the vector does not change. And then we have, when applied to 1, 0, we apply the CNOT gate, you will know our control bit here is equal to 1, which means that we're negating our second bit, in this case, when we preserve the probability amplitude. So we're negating our second value, which gives us a possibility of 1, 1, which makes us and allows us to say, hey, you know, once we apply this gate, what occurs here is the possible outcomes change a little, which means that half of the time still both qubits will come out to evaluate to be 0, but half of the time one qubit will come out to be 1, and the second one, rather than coming out to be 0, will also come out to be 1 as well, meaning both of them have a value of 1, which changes our particular values and changes essentially our perception and what the possibilities of what we measure and what the outcome will be. However, because we don't know precisely which qubit will correspond to which value, we can actually, because also we cannot assign individual states to the top and bottom wires, because again, this is based upon probability, we can really just write a bit of a bracket here combining both of them and write our linear combination for our two qubits here. And so this is what it will simply look like in terms of circuit diagram for a qubit when we're given a particular input of some sort, right, for top and bottom qubits, and we can actually use this to calculate possible outputs, and this is what the circuit looks like. Now, going back to this concept of the, I suppose you could say, the values of the vectors of which we're looking at, I'm seeing them, they change once we apply the CNOT gate. What it actually does in more official terms, it actually permutes our bases vectors, which means that it gives another set of ordered orthonormal bases, another set of, I suppose you could say, vectors in this case of 0, 0, 0, 1, 1, 0, 1, 1, right? It gives us another set of some sort. But note here that the order has been changed by a little bit. And that is essentially what makes a bit of a difference here. And again, I suppose you could say the resultant matrix representing our bases here is still an orthogonal matrix. If you note with our example of resultant value in our second linear combination here, once the CNOT gate has been applied, our second linear combination right over here, you will note again the order is slightly different, but they are still all mutually orthogonal to one another. They all correspond to an orthogonal matrix of some sort. And so this actually gives us the formal definition from a mathematical perspective of quantum gates. They're just operations that can be described by orthogonal matrices that allows us to say, hey, how is this orthogonal matrix changing when we apply the particular gate from a more physical perspective in terms of measurement, right? What we're doing here is we're actually changing the direction, not of the direction of measurement, but the direction the qubit is perhaps tilted in by a little bit. Alright, and so that essentially introduces the idea of the controlled NOT gate, works through a classical example, then works through a, I suppose, quantum example using, again, the instance of the circuit that we have currently right over here. And it allows us to essentially to see one instance in what happens when we apply a quantum gate of some sort, to a linear combination representing a qubit. So that is all for today. If you have any questions, please do not hesitate to check out the Q-munity Tech website. And as always, stay curious and keep on learning. Thank you.